In Module 4.3, we will look at flexibility options on the demand side rather than the supply side, especially demand response and sector coupling. Unlike with grids and storage, where we try to make the generation time series look more like the demand time series, here we are trying to reshape the demand time series so that it better matches generation. Now, of course, this demand side flexibility is necessary because the renewable generation from PV, wind, and to some extent from hydropower and other technologies like concentrating solar power is variable and not flexible. It's weather dependent, we cannot turn it on and off at will. We already discussed the fact that flexible generators like the ones here could help balance out the variable renewable electricity supply. But even if we don't have these flexible generators or we don't have enough of them, there are additional demand-side sources of flexibility. Here, we have an opportunity through the fact that many things are being electrified, and more will likely be electrified in the future. This is called sector coupling. Currently, separate energy sectors like heating private homes and fueling passenger cars are increasingly coupled by relying on electricity instead of other traditional fuels. So how does this bring flexibility? Let's start with just the electricity system. We already looked at ways to store electricity to balance variability. Now, if heating is increasingly electrified, it can become a source of demand-side flexibility. You can store heat quite easily, so heating systems can plan ahead and use electricity at those moments when it is abundant. Same with electric vehicles. They store electricity in their batteries, and you could set your charging system to only charge the car when there is an overproduction from, say, the solar panels on your roof. In addition, the cars themselves could act as batteries while parked and deliver electricity back to the grid when needed. Finally, power to gas. Generally, this means making hydrogen from renewable electricity, so-called green hydrogen. We talked about this already in the last module. You can store hydrogen and use it later to make electricity again. But you can also use it in the heating and transportation sectors, for example, to fuel airplanes in the future. Again, this can provide flexibility to electricity demand. You can produce the hydrogen when there is an oversupply of renewable electricity and store it for various uses, including turning it back to electricity when needed. It's quite straightforward to calculate how much extra electricity demand there will be when we electrify these things. But it is a lot more difficult to quantify exactly how much extra flexibility is available to have balanced variable renewable generation through this complex interconnected energy system. This is in fact still an area of active research. What is clear is that realizing any potential for demand-side flexibility through sector coupling must come along with a transition away from the traditional electricity grid. Remember, we talked about the traditional merit order of running power plants to satisfy baseload or peak electricity demand. This traditional setup is very top-down. A relatively small number of large, centrally controlled power plants are operated to always match demand. However, the grid is becoming increasingly smart. First, many small renewable generators spread around all over the place. And second, flexible demand sources like electric vehicles that can communicate with the grid to agree on when it is best to charge them. In the context of smart grids, you might also have heard about other kinds of demand response beside the sector coupling we discussed so far. For example, very small-scale devices like a smart fridge that could prioritize to run its compressor at times when there is an oversupply of renewable electricity. Or entire industrial facilities that could adjust their production schedule to decrease or increase their demand as needed. This is something that is already done today. For example, an electricity grid operator can pay a large industrial customer to reduce its demand temporarily when needed to stabilize the electricity grid. Such demand response, both at the small and the large scale, is unlikely to play a big role because of the limited potential to really shift demand very dramatically. You can't wait for days or weeks for your fridge to run. And with most industrial processes, there is also limited potential to just turn them on and off at will. Plus, the factory owners would like to produce and sell their product, of course. But still, this kind of demand response on a smart grid could help balance the very short-term fluctuations of renewable generation over seconds and minutes. Okay, so let's take stock overall. We discussed 3 different kinds of solutions to the problem of building a stable supply of electricity around variable renewable generation. Grids to balance through space, storage to balance through time, and flexibility, which is adjusting demand to balance supply. Conceptually, it is clear how these solutions can solve even the monthly to seasonal variability problem, partly individually and partly in combination. But there are many practical issues still unresolved. And because of the complexity of the problem, for example, the increasing interconnectedness of all energy-using sectors through electrification, figuring out how to put all these pieces together into a working system is not straightforward at all. So, in the final 2 modules, we will look at one way to plan how to put these pieces together: energy system models.